So energetics basically is one of the most important topics in ACE. So whenever we'll deal with some chemical reactions that involve any energy changes. You might have heard a concept of exothermic reaction or an endothermic reaction back in your O levels. These reactions, they basically, release energy to surroundings, and these reactions, they basically absorb energy from surroundings. So energetics is basically what we call about that those reactions that would have any energy change, whether it's release, whether it's absorption, that would be covered under energetics. Not obviously all reactions are basically chemical exo or chemically endo. Only few of them are chemically endo or exo. So we need to understand first that in energetics would involve all those reactions that have any kind of energy change during a reaction. That's one part. So now this energy change is basically in chemistry, we talk about as an enthalpy change or enthalpy change. So in simple terms, what is an enthalpy change? It's heat change that may be absorbed or released again in a chemical reaction. So we'll start up with different types of enthalpy changes. So first one is enthalpy change of reaction. Enthalpy change of reaction. So that basically deals with either heat absorbed or released. So for example, if we recall this reaction from our O levels, that's the formation of ammonia. So that would be enthalpy change of the reaction here, as this substance here can release some energy. So it's negative here. That is exothermic reaction. Another example can be sodium hydroxide aqueous reacting with hydrochloric acid aqueous to form sodium chloride aqueous alongside water liquid. So that would be enthalpy change of the reaction. So the pattern what we see here is the substance that is formed as a product is basically in the same state as the reactants were. Make sense? We were talking about ammonia gas. So we have ammonia in natural gas phase. We started up with nitrogen and hydrogen. They were present in the gases. Here we talked about being aqueous. Being aqueous means it's essentially a straight liquid, right? So reagents are obviously liquid, and then the product is in the liquid form. So that may accompany any enthalpy change. Then we have enthalpy change of formation. So this is if 1 mole of a substance is formed from its elements at standard conditions. So now what do we mean by standard conditions? Standard condition is by default RTP. RTP is referred to as room temperature pressure. And room temperature pressure is temperature of 25 degrees Celsius and pressure of 1 atmosphere. So let's say we take an example here, sodium solid reacting with chlorine gas, oxygen, gas, and it forms sodium chloride and AClO3 solid. So now what we think here is that substance which is formed is 1 mole, since it is 1 here, and then it is formed from its elements. All of these are in their elemental states. Sodium is an element here, chlorine is an element here, oxygen is an element here. They are not coming from any compound or molecular phase. You get this part?
Yes.
So let's talk about here. Here, sodium was not in the elemental phase. It was basically a compound, right? So we cannot use sodium oxide, sodium hydroxide here. That may lead us to the formation of sodium chloride. That is okay, but that would be heat of formation or enthalpy change of formation. So what we need to keep in our mind is if we are dealing with enthalpy change of formation, we need to have the elements in their elemental state. Let's have a second example. So hydrogen, gas, sulfur, solid, oxygen, gas. So we'll have H2SO4 liquid. So that would again be heat of formation because natural state, elemental state,
So what do you mean by elemental?
pure form. It is not
Okay.
combustion. Third is enthalpy change of combustion. So that is if 1 mole of a substance is burnt completely in the excess of oxygen. So what we see here is 1 mole, and that is produced from oxygen, and that substance is completely oxidized. So it won't be combustion if we are having something like this. Let's say C solid O2 CO. Why is that so? Because it is not completely burnt. It's limited supply of oxygen. So we need excess supply of oxygen to happen. So that won't be heat of combustion. Do you get this?
Yes.
Then we have enthalpy change of neutralization. So if 1 mole of water is formed, during a neutralization reaction, OH negative, H2O. So that would be enthalpy change of neutralization. That is small n, so sorry. And then number 5 is enthalpy change of solution. So when 1 mole of a substance that is an ionic compound is formed, is dissolved in excess of water. So H2O being liquid forms Na positive aqueous and it forms Cl negative aqueous. So this forms enthalpy change of solution. And then we'll have NH3 gas, H2O liquid, NH3 aqueous. Then we have the similar pattern, enthalpy change of hydration. So if 1 mole of gaseous ions are dissolved in large excess water, hydration. Then we have enthalpy change of lattice, number 7. So 1 mole of ionic compound is formed from its gaseous ions. So that would be enthalpy change of lattice. Then we have enthalpy change of atomization. One mole of gaseous atoms are formed from its elements. Then we have enthalpy change of atomization of compounds. Is completely converted into gaseous atoms. So that would be delta H atomization. So these are all basic enthalpy changes. Now, what we were doing with these would be that we need to understand the concept of some calculations that may be asked in questions, and that is what we are going to move towards that. So these all 9 cases, this is what I have written here, covers basically the entire syllabus. But now few updates of the syllabus, they say that few of these may not be asked in your exams, but that becomes irrelevant because questions we see in past papers, they cover all of these. So better be prepared for all these, all of these 9. We get this?
Okay.
Then we have few more things to go before we start up with questions. So first thing is we need to keep diatomic gases in our mind. So diatomic gases such as fluorine, chlorine, hydrogen, nitrogen, oxygen. So how do we calculate enthalpy change of atomization? So that would be their binding energy or bond energy over 2. Now what is bond energy here? So let's say if we consider any of one of these gases, that is F2 gas. We supply it with enough energy so that it splits up into 2 different atoms. So that was an F molecule. Okay. So energy supplied here breaks this at a link bond, and then we have F plus F. So whatever we supply it has been utilized to break this bond. So that is known as bond cleavage to break this bond. Do you get this part?
Yes.
So through this, we can infer that it is basically half F2G is equals to 1F. So that would fit in enthalpy change of atomization. This is what we have just done here. Okay. Similarly, if I ask you, where would you place this reaction? 1H2G, half O2G, and it forms 1H2OL. So it would be included in enthalpy change of combustion, since we say that it is basically excess of oxygen and it is basically completely being oxidized. Then it would be enthalpy change of reaction. What was enthalpy change of reaction?
Mm.
It may be an exothermic or endothermic reaction, right? So it is
Yes.
basically exothermic reaction. And then I can say that it is basically delta HF. That is enthalpy change of formation, because there is a substance that is formed from its elements. Do you get this?
Yes.
Okay. Let's do some more questions. So another example, if I say that I am having 1 carbon solid and half O2 gas, so this would be 1 CO gas. So where would you place this?
In enthalpy change of reaction.
So enthalpy change of reaction. And what else?
Formation as well.
Enthalpy change of formation as well. That's great. Anything else?
Yes. No.
That is good. Why is this not enthalpy change of combustion?
Because the oxygen is not fully burned.
That is so good job. So one thing that needs to be kept in mind before we move on is basically whenever we are discussing exothermic reactions, so we would be talking about bond formation being greater than bond breaking. That needs to be kept right in the center of my mind. And if you are talking about
Okay.
thermic reactions, so it would be reverse. Bond breaking would be more than bond formation. So we can conclude here is only bonds are formed, and here we can conclude that only bonds are broken. also. Now, what could you place here? Na positive gas, Cl negative gas will form NaCl solid. So what would happen here?
The bond forces. Oh, you're asking the enthalpy changes.
Yeah.
Hmm. Yeah, I didn't see the last one.
So this would be enthalpy change of lattice,
Okay.
and it would always be exothermic.
Okay.
Okay, then if we talk about strength, bond strength, so stronger bonds, they have more energy release. So we can say that strong bonds are formed with more release of energy. So let's say if there is a bond that is formed between monovalent cations and anions. So we consider this that let's say they release energy that is E. So if we are having a bond that is formed between divalent cations and anions, so this would be pretty much higher than what we have previously. So it's not always 2, it should be higher than this. That shows what? This being a stronger bond and this one being a weaker bond as compared to this. Do you get this?
Yes.
So we can say that if we are talking about lattice energy, so lattice energy is proportional to charge, more lattice energy, and lattice energy is inversely proportional to radii. That is, greater atomic radii would offer lesser lattice energy. Do you get this?
So more charge would mean more lattice energy, right? Or less?
Yeah, more.
More.
So
Okay.
let's say we write it in the way that. So let's make it, 1 over radii. Do you get this?
Yes.
Just a minute.
Okay.
Yeah, okay. So we talked about this. And then Yeah, it would be very good to mention here simultaneously that enthalpy change of hydration is still directly proportional to charge, and enthalpy change of hydration is still inversely proportional to radii. So lattice and hydration, they follow these essentially same trends. Okay, do you get this?
So it will be same in
For hydration
both,
and
right?
yeah.
Okay.
Okay, now we'll move towards the Hess law. So this law states that enthalpy change of a reaction
Okay.
is independent of routes taken to complete that reaction. So a reaction is completed in one step or the enthalpy change of the reaction stays constant. So let's say there is something A, any reactant, and it forms D, and the total enthalpy change of this reaction is, let's say, negative 100 kilojoules per mole. So now, according to the law, what we have discussed, if A forms first B, then B forms C, and then C finally forms D. So total enthalpy change of these three steps would be equal to what was happening in the single step, because A is ultimately converted into D. So let's say this would be minus 20, this would be minus 50, this would be minus 30. So you add this up, you'll get what? Same answer. You understand the law then?
Yes.
So if we say that what this law is all about, this law helps us to, break a very complex reaction into smaller individual steps. So we are going to go through these reactions in a while. So any questions so far?
No.
Okay, that is great. So let's do some questions. So if there is something A that converts to B and then B converts to C, that's the indirect step. However, the direct step is A being converted to C. Okay. So let's say this is given, which is minus 100, and this is given, which is plus 20. So how would I calculate the heat of reaction? This would be 9 minus 100 plus 20. So that would be minus 80. So enthalpy change for this direct step would be minus 80. Do you get this part?
Yes.
Let's do some other questions. So if A is there, B is there, and C is there. So B first converts to A, and then A to C. And then there is a direct step of B to C. And what we have is plus 100 here and plus 20 here. So how can I calculate the heat of reaction?
100 minus 20.
No, it won't be like 100 you said 100 minus 20.
Yes.
I don't know. So you need to understand that this is 100 and this would be HR, right? So 100 plus HR is equals to 20. So this would be delta HR is equals to 20 minus 100. That would be minus 80. You get this?
Okay. Yes.
Then if you talk about something like this, let's say. So we have A, we have B, and we have C. So B to A, then C to A, and then let's say B to C. So if this is 100, this is 20, and this is enthalpy change of the reaction. So how would we calculate it? So this would be 20 plus delta HR is equals to 100. So delta HR would now be 80. Understood?
But in this reaction which you made, sir, which is the direct one?
We need to understand.
Okay.
Where are you focused?
No, I understood what we did, but I was
This was
confused.
the direct one, right?
Yes.
How would you identify the direct reaction here? In the
B to
second?
C.
Yeah, that is correct. How would you identify the reactions here?
Both are making A.
How can you say this?
B to C again?
B to C? So this would be the
Oh,
direct.
no, B to A and C to A, right? Both.
No, it's only B to A. Now, why is that?
Okay, B to C,
If
then to
you
A. Okay.
follow this pattern, so B to A and then A to C is arrow directed towards A, not C.
Okay.
So these arrows are basically getting added up. That's the final result here. Similar is the case here. They are being added up. They are being added up. Do you get
Okay.
this?
Yes.
So let's do a question. So let's say if I say that we have sodium positive gas, chlorine negative gas, and it forms NaCl solid, and that is the enthalpy change of what? Lattice. Okay. So if we say that, okay, enthalpy change of sodium to sodium aqueous is calculated, and that would be enthalpy change of hydration. And then for chlorine aqueous will have enthalpy change of solution. So how can we create that equation here, which we were discussing previously? So can I say that you need to identify that what's the final part? So we'll start up with, it would be delta H by D hydration is equals to lattice plus solution. Make sense?
Yes.
So if they can ask me anything. If I ask you that, okay, tell me about what is this energy? So equation would be hydration minus solution. Make sense?
Hmm.
That is great. So now I think you will do some question now. So now I would give you a question, okay, and you need to solve it by yourself.
Okay.